user of this program? Okay. Continue. Okay, I'm otherwise not the user of this program. I'm using another program which was a part of the spectrometer. It's called VNMRJ. This program became also freely available now, but it's only available on Linux machines. So I decided for this snake, which is also a new and new program, looks quite capable, quite nice. But we'll only take a look at few most important features. So this will be one part of the, let's say, practical work. I mean, I hope you got yesterday also some test spectra or example spectra, so you will be able to follow what I will be doing and try to process the spectra yourself. And then in the next step, we will then import spectra into another program, into DMFit, which is especially convenient for analysis of solid-state NMR spectra. At the end, we'll conclude this session with a few words about assignment, how can we help ourselves when we want to assign signals in NMR spectra to individual sites in molecules or to individual crystallographic sites in crystals. During the session, I don't know, we'll have 2-3 breaks. If I forget, please remind me. If you have questions, either write them in the chat, either raise a hand, either turn on your microphone and shout something to catch my attention. Yeah, I hope that you heard me and that you agree with this. And if it's fine with you, we'll go to the introduction part. So to introduction to solid-state NMR. Good. I will share the screen. Let me find it. Should be this one. Okay. Yep. Okay. Good. Okay. I would just kindly ask if someone can let me know if you see the presentation well, as it should be.
Yes, we can.
Okay, great. Okay, let's start then. So, yeah, in my view, in NMR spectroscopy, NMR spectroscopy is a method that uses atomic nuclei as small probes which detect local environment or which detect local fields. And with local fields, I mean both magnetic and electric fields. And then through this information, then tell us something about the local structure or local dynamics. Now, of course, to understand what NMR spectra tell us about the local structure, we need to understand how these local magnetic fields affect the NMR spectra. And for this reason, we need to take a look at how these magnetic fields affect the energy level diagram of atomic nuclei. Because atomic nuclei are tiny, very small objects, we can treat contributions to their energy, contributions of magnetic fields and of electric fields to their energy through the so-called multipole expansion. With this multipole expansion, I mean, we can go in steps and take a look at more and more important contributions, starting from the monopole contribution, then dipole contribution, then quadrupole contribution. But in fact, in both cases, in case of magnetic and electric field, the first important non-negligible contribution is enough to completely describe the NMR spectra. So let's start with let's say, interaction of nucleus with the magnetic field or with the energy that the nucleus has in the magnetic field. So if nucleus has a magnetic moment, mu, then its energy in magnetic field is given like this, like a dot product with magnetic field. So its energy depends on the magnetic field. This is the dipole term because we don't have magnetic monopoles. Otherwise, the first contribution or the first term in the multiple expansion would be the monopole contribution. But for magnetic field, we only can start with the dipole term. And of course, in fact, energy, NMR should be treated by quantum mechanics. And such an expression, classical expression, is transformed into corresponding quantum mechanical expression in this way, so that the energy is transformed to Hamiltonian operator, magnetic moment is transformed to the operator of magnetic moment, and then further we can relate this magnetic moment operator to the product of gyromagnetic ratio, which is a property of a given nucleus, and its spin operator. And if we decide that the z-axis, laboratory z-axis, will point along the direction of magnetic field, so that B points along the z direction, then this interaction of magnetic moment with magnetic field can be described like this, with a simple and well-known operator, z component of spin operator. And for this one, we know what are the eigenstates. So eigenstates of such Hamiltonian are given by these eigenenergies, actually. So depend on magnetic quantum number, gyromagnetic ratio, and magnetic field. For a nucleus with total spin 3/2, then, for example, we get such energy level diagram. Of course, if we have only one nucleus, then it occupies one of these states and one of these levels. If we have an ensemble, and in the NMR spectroscopy, we always have a large ensemble of nuclei, then some occupy this level, some the lower and lower lying levels as well. And the most occupied is, of course, the lowest lying level. What's important is to learn from this that the difference between these energy levels, which is given by this expression over here, depends directly on the magnetic field. And this magnetic field is the local magnetic field at the position of nucleus. So if we are able to determine this energy splitting or this energy difference or the transition frequency between these two levels, we then indirectly measure the local magnetic field. Okay, this is the magnetic field contribution. And now I've mentioned that, I didn't mention that shortly back, nuclei, only nuclei that have, of course, spin quantum number larger than 0, so non-zero spin, have non-zero magnetic moment. Okay, now really to the electric contribution to the energy. In case of electric field, we, of course, do have electric monopoles. These are electric charges. So we start this expansion, this multiple expansion, by the monopole term, which is simply the product of the charge of the nucleus and electric potential at the position of the nucleus. This is fine, but this term doesn't affect the differences between the energy levels, because we can easily see that this term doesn't is not affected by the orientation of the magnetic moment or of the spin. So in other words, it doesn't depend on magnetic quantum number. So it only shifts all the energy levels equally and does not affect the transition frequency or the energy splitting. So by NMR spectroscopy, we therefore cannot determine this interaction, or we cannot determine the electric potential. So we have to go to another term. This is the dipole term. But the dipole term well, of course, the form of the dipole term is the same as the form of the that we encountered in case of magnetic field. So electric dipole moment dot product with electric field at the position of nucleus, of course. But this term is actually always equal to 0 for two reasons. First, electric dipole moment of a nucleus is 0 because atomic nuclei are symmetrical objects which have center of charge at the same position at center of mass, so their dipole moment is 0. And also, usually in equilibrium, also atomic nuclei stay at the position of the 0 electric field. So if the electric field was not 0, then there will be the force acting on a nucleus, and the nucleus would be moving. But typically they're in equilibrium state, and so both contributions to this part are 0. So if we want to learn something about the electric field at the position of the nucleus, we have to consider the next term in the expansion, and this is the quadrupole term. And this term looks like this. And in this term, we have a product of electric quadrupole moment, which is here, and the electric field gradient. So this is the first term that we really can detect, because this one does affect differently energy levels with different magnetic quantum numbers. So this term raises energy levels of for some magnetic quantum numbers and lowers the energy for the other quantum numbers. So it does affect the transition frequency. So we can detect this contribution to the transition frequency or to the energy splitting. What I should note here also is that only nuclei that have spin quantum number larger than 1/2, so spins with 1, 1.5, 2, 2.5, and so on, such nuclei have electric quadrupole moment. Nuclei with spin 1/2, like hydrogen nucleus or carbon-13 nucleus, are spherically symmetric nuclei and don't have electric quadrupole moment, so such nuclei cannot probe the electric field or the gradient, electric field gradient. But nuclei like aluminium, lithium, sodium, and many, many others can. Okay, so basically, to summarize, the energy of nucleus in a magnetic field is given by the dipole contribution to the magnetic energy and quadrupole contribution to electric energy. Or in other words, from NMR spectroscopy, we should be able to learn about the magnetic field at the position of nucleus and electric field gradient at the position of nucleus. The latter is determined by the charge distribution of charges around nucleus, and the former, so magnetic field, is actually determined or can be determined by many different contributions. The main one and the largest one is of the superconducting magnet, which we are generating with our magnet, which is part of the spectrometer. But then, because of this magnetic field, electrons start to circulate around nuclei and generate electric currents, and these electric currents generate weak magnetic fields which try to shield external magnetic field. This is the so-called chemical shielding contribution. Then also a nucleus, let's say under observation, is surrounded usually by many other nuclei which can also have magnetic moments. And if we have a magnetic moment, so as a bar magnet, also tiny nuclear magnetic moment also generates magnetic field. So magnetic moments not only can detect magnetic fields, but they also generate magnetic field. So our, let's say, detector detecting nucleus also detects magnetic field of neighboring nuclei, and even more, it can detect magnetic field of unpaired electrons, which are 3 orders of magnitude larger than typical nuclear magnetic moments. Okay, how this individual, now I will not have time to further discuss electric field gradient contribution, but I will say a few words more about the different contributions to magnetic, to local magnetic fields. How these different contributions affect the transition frequency or the energy splitting. Well, for the external magnetic field, the situation is simple. So energy splitting or transition frequency is simply given by the product of the gyromagnetic ratio of a given nucleus, and external magnetic field B0 is usually denoted. Gyromagnetic ratio are the properties for a given isotope. They can be quite different. And this leads to different Larmor frequencies for different isotopes. In our spectrometer, we generate magnetic field of 14.1 Tesla. So protons in our magnet have Larmor frequency of 600 megahertz. Carbons have 4 times lower Larmor frequency. Nitrogen 15 have 10 times lower frequency, and so on. Now, if this was the only contribution, so if we only detected external magnetic field with our nuclei in a molecule or a crystal, then NMR would be rather useless, right? Because then, for example, all what we could see for such a molecule in a magnetic field, we could see 4 different contributions, one belonging to all 3 carbon nuclei, then 1 signal for all hydrogen nuclei, 1 signal for all oxygen nuclei, and 1 signal for all nitrogen nuclei. The intensities here are not in the proper ratio because, of course, hydrogens are almost, hydrogen 1 is almost 100% abundant in nature, whereas carbon 13 is, for example, 1% abundant, oxygen 17 even order of magnitude less abundant in nature. So usually then we detect very, very weak signals for some nuclei. But luckily, so external magnetic field is not the only contribution to magnetic field. I've previously just mentioned that a very important contribution is also the one of the circulating electrons around atomic nuclei. So electrons circulate around atomic nuclei when we put the sample into magnetic field. So this is the diamagnetic response of a matter of electrons to the presence of magnetic field. In this is seen in the expression how these circulating electrons or these electric currents affect the transition frequency. So they affected that there are 2 parts of this chemical shielding contribution. This one is called the isotropic contribution, and this other longer part is called the anisotropic contribution. What we can immediately see is that both actually contributions are proportional to Larmor frequency, or in other words, they're proportional to the external magnetic field. Therefore, if the sample would not be put into external magnetic field, this whole contribution would be 0. So we wouldn't have this chemical shielding contribution and we wouldn't have chemical shift. That's why it's important that we have, even though we want to detect local fields, we are not interested in B0, but we need to put sample in large B0 so that we also have large chemical shift contribution. Okay, first to this isotropic part. In addition to Larmor frequency, it is also proportional to the isotropic value of the shielding tensor, the one parameter, sigma iso. It's not that important now, but what is important is that this parameter depends on the local environment of a nucleus. It depends on its chemical environment, on the crystal or crystallographic site, so different nuclei on different chemical parts of the molecules or on different crystallographic sites will have different value of sigma iso. So, and therefore, for example, for carbon part, here in this spectrum, we should see 3 different signals because we have 3 different types of carbon environments, carboxylic, this middle one, metal. And this is actually what we really see in solution NMR. So we see this contribution, but we don't see this second contribution. What is this second contribution? Well, here we have two more important parameters, delta and eta. The first one is called chemical shielding anisotropy, and the second one, chemical shielding asymmetry parameter. And this, in the same way as sigma iso depend on the local environment, these two also depend on the local environment. So again, for nuclei on different sites, they will have different values. But what is also, or for the moment even more important, is that they also depend on some angles. This contribution depends on some angles. These angles determine the orientation of a molecule or of a crystallite or fragment of the crystallite with respect to the external magnetic field. So for molecules that are differently oriented, this contribution will be different. In solution, of course, molecules at every instant time are different. There are molecules which are differently oriented in the sample. But these molecules rotate very quickly, so that on the NMR time scale, their contribution, this anisotropy contribution is averaged out. In solutions, we do not see this second part of the chemical shielding contribution. We only see this part, and therefore we see such nice, well-resolved signals for nuclei in different environments. In solid state NMR, the situation is different. Of course, I have to mention that NMR is not a very sensitive technique in the sense that a single nucleus or a few nuclei give very, very, very weak signals. So we always need a large number of nuclei to produce or to detect a reasonable signal. That in solids usually means that we have to work with powders, with polycrystalline or material, or with material with many particles. And if we have many particles, these are usually oriented in many different or all different possible directions. And so we will have contributions with different theta and phi values. And therefore, in the NMR spectrum of a solid, for example, for this contribution here, we will actually not get just contribution at this frequency, which is determined by sigma iso, but for one orientation, for example, for one orientation of molecules, we will, because of this additional contribution, we will get a signal here. For another orientation, we will get a signal slightly displaced. For another contribution, again, slightly displaced. And so for all contributions for theta ranging from 0 to 180 degrees, for phi ranging from 0 to 360. So we will get a spread, actually a spread of line, a distributed line, a broad line, which we call a powder pattern. And of course, we will not get this just for one site, we will get this for all three sites for this particular case of alanine molecule, which I'm showing. So this is, in a way, this is a complication. Although in another way, this means that solid state NMR spectra in principle offer us additional information. So they offer us not only information on the isotropic shift, but also on the anisotropy and asymmetry. So they, in principle, can tell us more about the local environment around nuclei. But of course, the problem comes first, because usually we don't have such simple cases with only 3 signals. But even if we do have simple cases, chemical shielding contribution is not the only contribution. I've mentioned before that we also have contribution of neighboring nuclei. And these, again, are anisotropic in nature. They don't have an isotropic contribution, so there is no shift as it is in the chemical shielding case. There is only anisotropic contribution, which broadens the signal if we're dealing with powder. And it broadens it in a, if we have, let's say, well separated pairs of nuclei. So one pair of nuclei here, one pair of nuclei far away, and another pair of nuclei far away. Then all these pairs of nuclei in differently oriented crystals will give us this nice line shape, again, powder pattern, which from this shape, we are able to determine this anisotropic parameter, which we call dipolar coupling constant. This is interesting because dipolar coupling constant is directly proportional to the distance between the two nuclei. So if we have an ensemble of, let's say, isolated nuclear pairs, we are in principle able to measure such powder patterns and determine distances between nuclei. But there's, again, a complication. Usually, we don't have only one nucleus as a neighbor to this nucleus which we are detecting. We have another nucleus here, and another here, and another here, and another here, and so on. And then we have to sum up all these contributions together. And then, because we have a large sum over many nuclei at different distances, so with different dipolar couplings and with different angles, we then end up, instead of such determined line shape, we end up with a Gaussian, broadened Gaussian line shape. And again, of course, this, for our case, for all three sides. So there are already two ways that are two contributions that broaden the spectra. One is chemical shielding. I'm showing here just this effect. One is dipolar coupling, so contribution of neighboring nuclei. I'm showing just this second effect. And now in reality, for these crystals of alanine, we have both contributions at the same time. So broadening because of dipolar coupling with neighboring nuclei, and broadening because of chemical shielding anisotropy, and we get this spectrum. So instead of resolving contributions of three different carbon atoms, we get a broad unresolved signals, and this one, although in principle contains a lot of information, we cannot extract information out of this such a spectrum, right? So what to do? We know from solution NMR, where we have a good resolution, but no information on anisotropic interactions, that in that case, we still can get a lot of information by cleverly designed NMR measurements, a lot of information about the structure. So also here, we can expect, if we can somehow increase resolution, remove broadening, that we might be able to help ourselves. And to remove anisotropic interactions, we try to mimic fast orientation of molecules in solution. That is, we try to spin samples very, very quickly. And what does this spinning does? Well, very quickly, for example, for the dipolar contribution, when we spin the sample around the selection rotation axis, it then doesn't depend if the orientation of crystallite is such that theta is this value, or that theta is this value, or any other value. In any case, this vector is circulating or precessing around this axis. And then if rotation is fast enough, then on the average, we will see, or this nucleus will see another nucleus as sitting on this axis of rotation. So for all the crystallites, then the average picture will be the same, will be like this. So we will not be dealing with a, let's say, distribution of theta ij angles, but they will all have contribution equal, which will depend on the theta r angle, so the angle between the axis of rotation and the external magnetic field. And now if we're clever and select theta r such that this whole term in the brackets will be 0, then, we remove this anisotropic broadening. And with one single angle, 54.7 degrees, which we call magic angle, with one single angle, we remove the broadening from this neighboring nuclei and from chemical shielding, and to some extent also by electric quadrupole interaction, which I will not have time to talk about. Okay, and that is why the magic angle spinning approach is, let's say, more or less the basis of almost all solid state NMR measurements nowadays, especially in the field of material science, not so much in the field of physics, but in the field of material science, we almost always use magic angle spinning in addition to other techniques. Okay, how do we do that? How we spin the samples actually? Well, we put the samples into NMR probe, which we then insert into the magnet, and an NMR probe contains a part which we call stator, and in the stator we insert this white is a ceramic tube, usually zirconium tube, which is hollow, and into which we pack the sample, the crystalline powder or the amorphous powder or whatever. So we put the sample in this zirconia tube, which we call NMR rotor, and then we close this rotor from one side with a cap and from another side with a turbine. And then we blow air or nitrogen or other gas into this turbine, and this causes this rotor to start spinning very fast, rapidly. And this rapidly means from several kilohertz to several tens of kilohertz, or even above 100 kilohertz with nowadays most recent probes. Okay, this is how we do it, and this is now the effect. Okay, if we spin sufficiently fast so that frequency of rotation is comparable or larger than the width of the static line, then we practically, because of this spinning, end up with very well resolved narrow signals only. If we don't spin that fast, then we will see also some additional signals in the spectrum, which are, however, linked to the main signals. They're displaced from the main signals by the multiple of rotation frequency. In this case, that I'm showing, the rotation frequency was 2.5 kilohertz. So these signals here are displaced by 2.5 kilohertz. These signals here again are displaced by 2.5 kilohertz. Now this can sometimes be regarded as, let's say, complication of the spectrum, but in other cases, we can use these intensities of this or this pattern of these signals to not only deduce the isotropic position, so the position of the one signal which we see with very fast spinning, but also to deduce information on chemical shielding, anisotropy, and asymmetry parameters. So for delta and eta, which I've showed before in the equations. Okay, so this is, okay. This was very briefly to give you some impression about the difference between solution and solid state NMR, and that in solid state NMR, we could deal with broad spectra, but typically we rotate the samples and therefore we get well-resolved spectra, but we are still often interested in other parameters than just the isotropic shift. Now, if you have a question for this part, you're welcome to write it or ask by turning on your microphone. I hope that you could follow, that the sound and the picture was good. So if anyone has a question, please ask. Otherwise, we'll then move to another part. Okay. Seems that you're either tired after lunch or everything's clear, or okay. Okay, thanks for the comment. Good. Then I will now show you a 15-16 minutes long video, which I already mentioned before, where you will see how we prepare the samples. I hope that projection and voice will work fine. I just have to find it. No. No. Where show all windows. This is where do I have? No, it's not this. This one, it's this one, yes. Share sound. Okay, it should be this. I hope. Okay, I will start. If you don't hear the sound or something seems to be wrong, then please turn on mic and shout and tell me.
Hello, and welcome to Slovenian Nmr Center, located at National Institute of Chemistry in city of Ljubljana within Slovenia. Let's have a look. So here is located the laboratory for solid-state nuclear magnetic resonance spectroscopy, where we mostly measure solid samples. Here, we normally prepare our samples, we grind them and fill them in specialized rotors, which are then put into the heart of the magnet of the spectrometer. Here, we usually produce experimental pulse sequences for our experiments and also analyze the data. Here is the heart of the spectrometer called the console, which is the source of radio frequency pulses with which we excite the nuclei and then also record the signal coming from our samples. Because we can spin our samples with high frequencies, we also have the automatic control system, so we can leave our experiments over the night or over the weekend if they are longer. We can also control the temperature and do some temperature-dependent measurements. In this room, we have a superconducting magnet that produces a magnetic field of 14.1 Tesla, which is roughly 500,000 times stronger than Earth's magnetic field. The magnet is quite old and unshielded. We keep it in a separate room for safety reasons, away from most of the electronics. Also, when changing samples, we leave our wallets, smartphones, watches, and keys outside of this room. Now I'm going to show you how to fill a rotor and what components it's made of. So first and foremost, we have the main part, which is made from zirconium oxide ceramic, which is very strong and hollow, so we can put in the sample. At one end, we usually put in the separator, so we don't need as much sample, and a turbine, which enables us to spin the rotor. And on the other side, we put in the cap to seal it completely. We're going to fill one rotor with this blue sample, and as you can see, the crystals are quite large. And what we want is to have as small crystals as possible, so that's why we're going to grind them out into finer powder. Once the powder is grinded, we can then start filling up the rotor. And before that, we put in the separator. Just push it in gently. And the turbine. Then put it in the special holder, which will hold the whole rotor in place while we fill it with the desired sample. We take some sample and put it in and just gently tap on it so the sample slides into our rotor. After we do that a couple of times, we push the sample with another tool. So we pack the rotor with the sample as much as possible. In other words, we squeeze the sample to the maximum density. At the same time, we can also check with this tool if the rotor is full or not. We still have some space left, so we're gonna put some more sample inside. And again, we push the sample in, and at the same time check if there's enough sample inside. After we fill the rotor with our sample, we put on the cap to seal it completely from the other side. At the end, we also color the rotor with two different colors so that we can follow the spinning rate with the laser detector. We use silver and also black color to give a contrast. Then we inspect the cap. If we colored it completely around and around, and if the border between one and another color is sharp enough, as we can see, it's colored nicely. And the last step is just to push the cap in as far as it goes to seal it completely. And that is prepared rotor, which then we can put into the magnet. So now I'm going to put the rotor into the plastic container. So we can label it and not mix it with others. Afterwards, when we have our experiment ready, we will put the rotor inside the magnet and measure a spectrum. Now we're going to spin our sample. First, we're going to spin to 5k hertz, and if the spinning is stable, we're going to slowly increase the spinning rate up to 20 kilohertz, which is our target spin rate. As seen, the spinning is stable, so now we've inputted our targeted 20 kilohertz and slowly rise up to the spin rate for our experiment. Now that our spin is stable at 20 kilohertz, we can measure our first spectrum. But before we can actually do the experiment, we have to tune the probe to the alarm frequency of the nuclei that we're going to excite. And this is done right below the magnet. Now we're going to measure our spectrum. The last step between starting the experiment, we check the pulse sequence and if we will excite the right nuclei within our sample. Then we start the experiment and wait for the free induction decay signal to be measured. This is our signal in time domain, which is then Fourier transformed into frequency domain into our desired spectrum. And this is the spectrum of our sample, which can then be further analyzed. We have 3 different probes for 3 different sizes of rotors. The largest one with 6 millimeter diameter, 3.2 millimeter diameter, and the smallest one with 1.6 millimeter diameter. The smallest one is for highest spinning frequencies, up to 40 kilohertz, and the largest one is usually used for low gamma nuclei. Let's check the probes. So here is the probe that we use for 1.6 millimeter rotors. The probe used for 3.2 millimeter rotors is currently installed inside the magnet. And this is the probe for 6 millimeter rotors. The very top of the probe contains a stator in which we put our sample in the rotor and spin them at high frequencies. This stator is tilted at magic angle relative to the external magnetic field. I hope you've enjoyed our short introduction to NMR experiments, and thank you for your attention.
Okay, I'm back. I hope that you liked the video, that it was clear. So probably now you have some questions, or am I wrong? So please, yeah, if you have some questions, please ask them, write them down, or yeah. Okay. I see or hear no questions for the moment. I hope that this is because everything is clear and not that everybody is missing. Now, if you want, we can do a short break of 5 or 10 minutes, or we can proceed. I don't know. What would you prefer? Any opinion? Do you need a break?
Maybe a short break would be great. Thanks.
Okay. Then let's have a 10-minute break, and let's get together back at 3:10. So I'll write in the chat also. Okay, we're back. Has any question appeared in the meantime? If not, I will just show 2 slides to discuss Fourier transformation, signal processing, and then we will really go to the first program, Snake, to learn how to transform the raw time domain data to the spectrum. Okay, no questions, I guess. So let me continue. Oops, what's this? No, this one. Okay. Yeah. Okay. In the short video, at the end of the video, you've seen that my colleague recorded a very quickly recorded an NMR spectrum that was spectrum of protons, which have a strong signal. And the first thing that we get is directly from the measurement is a so-called time domain signal. So we do not, in modern NMR, we do not measure these, let's say, transition frequencies or energy splittings in a way that we would slowly sweep the frequency of your radiation and see at which frequency we have a larger absorption of energy and at which frequency we don't have absorption, and so that we would obtain signals in this way. We are using so-called pulsed NMR. So we are using short pulses to excite nuclei. We select a certain Larmor frequency for a certain nuclear type. For example, if we want to observe the part of the spectrum which belongs to carbon nuclei, we select 150 and something megahertz in our case as a radiation frequency. We use short pulse, and with this short pulse we excite a certain spectral width around the excitation frequency, and then we monitor the response of nuclei. In fact, we monitor the precessing magnetization in the sample, which induces, because it affects the, let's say, magnetic flux through the coil, which is wound around the sample, so, and induces voltage in the coil, and we pick up this voltage, detect this voltage, convert it to, or digitize it, and then we have something that we call time domain signal or free induction decay. And of course, the way this, the time dependence of this free induction decay actually contains information about the frequency contributions in the, to this signal. But to analyze these contributions, what frequencies are present there, we need to do some kind of spectral analysis, and this is of course conveniently done by Fourier transformation. Typically a time domain signal looks something like this, but this is much simplified because it shows the signal of only one species. Usually in a sample, we have contributions from different nuclei in different environments, and such nuclei then their signals oscillate at different frequencies, and then this all sums together to a more complicated time domain signal. But for one contribution, it should look like this. So something oscillating, and of course, these oscillations don't go forever, but they are in reality damped by the relaxation time, which can be exponential, which is usually exponential. Okay, in practice also, we actually don't measure only one signal. We also measure a signal that is 90-degree shifted from this signal. We call the first signal a real part, and the second one the imaginary part of the time domain signal, and together they form a complex signal which can be, let's say, analytically, ideally described like this. And then we do, to analyze what contributions are present there, we do Fourier transformation. So Fourier transformation of such a signal would give such a result. So would also give us a complex function. So you see we have a real part and we have an imaginary part of the spectrum at the end. And this function is called Lorentzian function. So Fourier transformation of an exponentially decaying function is a Lorentzian function. If this decaying would be Gaussian, then Fourier transformation would also give Gaussian line shape. Okay, so the two components, the real and imaginary, are also referred to absorption component and the dispersion component. So absorption component looks like this. So symmetrical, relatively narrow, but if it's a Lorentzian line, it has still quite long tails. But the dispersion part, so the imaginary part of the obtained spectrum, has even longer parts. That is why typically we only look at and show in the papers and presentations, we only look at the absorption part of the spectrum. I mean, information is basically the same in the two parts, but this one is easier to analyze, and it's easier. We more easily resolve different contributions here if we have more signals close one to another, because they don't overlap that much as they would in this case of the dispersion shapes of the lines. There is one more thing I should note, that in reality, very often we don't get, after Fourier transformation, entirely clean absorption spectrum. It could be that there is an admixture of dispersion part in the absorption spectrum and vice versa. In the dispersion part of the imaginary part of the spectrum, there's a mixture of absorption and dispersion also. This is because it could be from different reasons, but one certain reason is the dead time problem, because we are exciting nuclei with a short pulse, with quite high voltage in the coil. Then immediately when we turn off this voltage, of course the voltage doesn't drop to zero in infinitely short time, but it needs some time to drop to a sufficiently small value. And then with the same coil, which was used for exciting the nuclei, we also detect the induced voltage. And this induced voltage is much, much weaker on the microvolt level. So we need to wait a few microseconds after the pulse to be able to start detecting the pulse. And because of this dead time, we don't do Fourier transformation actually from zero time, but we do it from with a little bit delay, and this delay introduces a so-called phase error, and we do need to do phase correction. This will be one thing which we will also meet now when we go. Screen sharing has stopped. Okay, yeah, when we will go to our first program. Okay, and this first program is one that is called Snake. So this one. Okay. I hope that you see it. Okay, there's already a spectrum shown here, but I will close both spectra and we will start from fresh. Now, as you like it, you may try to do, if you can, the same as I do, or you can just watch what I'm doing and play with the program later on. As I said, this is not the program that I'm really working on, so I'm not very, very familiar with it, but I know how the basic things are done here, and you will see that the basic things are done very easily. Of course, the program offers more things, but you can learn these things later on if you will need them. What you need to do, well, I hope that the colleagues, the organizers of this school have sent you some files with some spectra which I prepared, so that you have something to try to work on. I have this spectra in this folder, and we will start with the carbon spectrum, which is in this folder, carbon 13 MAS 16K. So these four folders, aluminium, carbon, fluorine, hydrogen, 5 folders, deuterium, H2. These are the data, the raw data as obtained from the Varian NMR spectrometer. So Varian NMR spectrometer saves the data for each spectrum that we record, makes a folder. And in this folder, I will open this with carbon 13. And in this folder, it gives several files, actually to our, not from Varian, but from our previous analysis. But the files that Varian puts in are the FID file, log, protspar, and text file. Now, the FID is the main part. This is the raw data. This is the time domain signal in binary format. Log file summarizes some actions during the measurement. Protspar lists all the parameters, the type of parameters, their values. 95% or more percent of these parameters are not needed for the measurement, for the given measurement or for the processing. And text is something that you write when you want to describe what you've measured. So for our purpose, this file FID is important. And here, so we, in this file selector, we select this one, confirm, and there we go. We have immediately what we see is a time domain signal. Actually, it is a real part of time domain signal, a real part of the FID. Snake offers us also to show, to take a look at the imaginary part, or to at the same time see both parts. So blue is real, orange is imaginary, but not to have too much mess, we will just show the real part. As you see, this is not perfect cosine or sine function. This is because this, as we will see after the transformation, there are several contributions with different frequencies present here. And as you also see, this signal drops on a time scale of milliseconds. So this is quite typically for NMR's signals, that they last from somewhere from microseconds to milliseconds. Now, probably you know Fourier transformation that much that you know that if the signal is longer or lasts longer in time domain, then Fourier transformation will give narrower signal in the frequency domain, and vice versa. If we have a signal that drops very quickly, then this, after Fourier transformation, the corresponding spectral line will be very broad. Okay, this is it. What we also see here is Larmor frequency, or the frequency with which we irradiated nuclei, so 150.8 megahertz. So this was on our spectrometer, this corresponds to Larmor frequency of carbon nuclei. So this is the area where we see what we are doing, and there are some quick buttons over here which we can use for doing the most common task, and there are some additional tasks on the here on top line. So very quickly we will get the spectrum if we simply push Fourier here, so do Fourier transformation. Yeah, here we also see that the program automatically detected that this is the time domain signal, and after Fourier transformation we got a spectrum, so frequency domain signal, or the spectrum simply. Yeah, currently the axis is given in kilohertz. Typically NMR spectra are plotted versus ppm, because then the positions of the signals should be the same regardless of the spectrometer which was used, so regardless of the strength of the magnetic field. If we have axis in kilohertz, then if we use twice stronger magnet, we will get twice larger shift in kilohertz. But in ppm, which is a deviation from a reference signal divided by Larmor frequency, then this is not the case. Now, with this Fourier transformation, we see that we got a very, let's say, twisted spectrum, okay? This one is especially turned upside down, but here we see those features which I've mentioned at the end of my previous short presentation. So these signals have mixed absorption, dispersion character. And we have to do phase correction to transform this signal into a proper absorption shape. This phase correction either works on time domain data or on already Fourier transform data. In both cases, it combines both real and complex data to get to the right result. And in this program, the snake program, we can push this button or open phasing window over here. Now there are 3 parts of this opened window. We can, for example, first pick a pivot line. I don't know how to describe it, but if I push this button and then move cursor inside the box, then I will, let's say, move on to one of the signals over here. So I will start playing at this position. And because I picked a pivot line over here, then by changing phase 0, I will mostly affect, or I will try to put this, to transform this shape into pure absorption shape. So of this signal where I've chosen a pivot line. So I have to go to the left side to get the approximately convenient shape. This is not far from being perfect, but then I will try to make it better with changing also the first order correction, phase correction. And indeed, if I go to the right, obviously, if I went to the left, then I would still further spoil, I see. But it's something you have to try, right? What way is the right way? Now with this, we've come to a pretty nice spectrum. I'm satisfied with it, so I'll push OK. Now it's a little bit off, horizontally shifted. So I will zoom it in. And I would also like to mention here that typically NMR signals of carbon nuclei fall between 0 and 200 ppm, rarely out of this area. We have some signals over here in this particular case, but these are actually the spinning sidebands that belong to these 2 signals. And we have spinning sidebands also here below and here below. So I will just zoom to this part for now, which is, let's say, the most informative for us. And okay, we already have a quite nice spectrum. This would be, we could be quite satisfied with it. But in principle, there are sometimes other things that you have to do when you do such, when you're processing the raw data. Now, the baseline is pretty flat, but if it wasn't flat, then you might want to correct it. I guess here in Snake, you do it by going to the Tools menu and do select baseline correction. There are 2 types in this case. Polynomial is fine. And then you pick places where you have signals. So you click on one part and say, okay, I have a signal here. I have a signal here. I have a signal here. Okay, all this area are signals. This is a small signal. These are also signals. Okay, so this, I will say, these are the signals, and the rest should be treated for the program as part to which the baseline should be fit by polynom. Okay, and this should be at the end, if baseline correction is working well, it should be flat. In our case, it is already flat, so this will probably do nothing, but in principle, if it was twisted, if it was wavy, this should flatten it by using a polynomial fit to it. And we did okay, now nothing happened. Otherwise, you can quite efficiently correct baseline also in DM fit, which we will use later. Okay, this is one of the tasks. So phasing, baseline correction. Then sometimes the spectrum can be very noisy, or the time domain signal can be very noisy. And if it's useful, if we, at the end, cut this noisy part that doesn't bring any information about the oscillations, if we cut it out. And we do in practice this by applying windowing function or by doing apodization. In Snake program, we do apodization by choosing this button. Now this apodization is actually done on time domain, not on frequency, but we will see by doing it, actually the snake will immediately apply it to the time domain and immediately do the Fourier transformation, and we will, let's say, on the fly see what happens if we apply apodization function, what will happen to the spectrum. So we can choose the apodization function, could be Lorentzian, Gaussian, something else. If we choose Gaussian, okay. And then we use the slide bar and apply, let's say, narrower apodization function in time domain, which means that we will apply more and more broadening in frequency domain. So with very light gray, we see the remaining, the signals as they were before. And these are the signals that we obtain if we apply apodization function. In this particular case, we see that it was too drastic apodization because we lost resolution. Actually, in this case, where we have quite well recorded and low spectrum with low noise, there is not real need for apodization, but perhaps, okay, let's choose a weak weighting function. But of course, as I said, apodization is fine for bringing smooth curves, but we have to be careful with it because we can completely lose resolution and the spectrum becomes useless. It's more useful when we have really noisy data. In our case, these are not very noisy. Okay, so we said phase correction, baseline correction, perhaps apodization if it's needed. One thing which we don't see now, but we will see if we zoom to, for example, one single peak, is that how fine the peaks are defined. Now, those of you who know Fourier transformation better know that so the resolution, the digital resolution of the spectrum, so the separation between 2 points in the spectrum, is given by the length of the time domain signal. So if we recorded time domain signal to 15, I don't know, to 10 milliseconds, then digital resolution will be what, 100 hertz or something. So it's inverse value. So we cannot go better. But in fact, if we can improve this digital resolution and we don't bring any physical new information, but we change the appearance of the spectra by simply adding zeros to the end of the time domain signal. So we don't bring any new information, but because we're extending the time domain signal, we will get more points in between. And to do this, we can use this button, 8K or set size, and we will first reduce the number of points used in the Fourier transformation to see what happens. So if we are reducing the number of points, so less and less points determine our signal, but we are increasing the number of points and we are starting adding points at the end of the time domain signal. We are getting smoother and smoother signal. And it seems that about 16K is completely enough, or perhaps already 8K points is completely enough to get smooth lines in this particular case. I mean, we can add more zeros and increase this digital resolution, but if we are then exporting such a spectrum, such as into an ASCII file or something, then we're just having too many points which tell us nothing. So it's not useful or meaningful to increase this too much. It's just so that is enough. So 4K might be too little in this case. 8K seems to be enough. It's okay. If we double click with the right mouse button, we return to the to this part. Okay. So I guess, yeah, this is how the spectrum looks. It's, I guess, pretty nice, something that we can, in principle, be satisfied with. Just for practice and for pointing out another feature, we will open another spectrum, and this will be a spectrum H1 MAS 20K. So I will open another spectrum. Okay, now I have two. So I have two sets of data. So I still have the carbon spectrum in this window, and I have so far only time domain signal in this window. Now I will show you why I would like to share this example with you. This spectrum was recorded a little bit different than the previous one. If we do Fourier transformation of this one, we can get a twisted line, and then if I want to correct this face of this line, you will see that no matter how I change the face, oops, where do we have it? I cannot make a proper absorption line for this. Well, with a very drastic phase change, I could, but this is not what I want. I will go back to this. Okay, I hope that this is okay. The reason for troubles that we have is because, if I take a closer look, because this spectrum was recorded with what we call echo sequence. Now, before I've mentioned that in NMR we can have a so-called dead time problem because we cannot start recording immediately after the pulse. But with a special approach, if we use proper two pulses, we can form an echo, so a signal which will not start decaying immediately after the second pulse, but it will first, after some delay, it will first start to rise, and then it will start to fall as the original free induction decay. And then we are not limited by the dead time problem because dead time was here in this initial part, and when we started recording, we actually were still in the rising regime, and then it starts the falling of the FID. And now if you want to have a good phase and a good baseline, we just simply need to move to the top and start Fourier transformation from the top of the echo, from the top of this signal. And then because we will not have a dead time problem and not, so it will be as we started the Fourier transformation at true zero time. And how do we move? Well, we use this arrow button here, which, whoops, where are you? Which offers us shifting data, and we will, not in the right direction, so we will move so many points that we will start from the top. So when we start decreasing the signal, we will be already too far. Now it was decreased. Okay, here is the top of the echo. And if we start Fourier transformation from here, we should immediately obtain well-phased or pure absorption spectrum. Okay, let's try if I'm correct. So I will accept this data shift and do Fourier transformation. And indeed, in this case, we get a very well phased, a very well shaped spectrum like this. Okay, this is a proton spectrum. In proton spectrum, you can see that the lines are broader than in the carbon spectrum because there are several reasons. One is because of strong dipolar coupling. The other one is that if I turn the scale to the ppm, the axis, you see that most of the signals in proton spectra are gathered in a very narrow chemical shift range of about 10 ppm, whereas in previous case, for example, the signals are typically spread over 200 ppm. And there are, of course also narrower by themselves. Okay, I guess this is something about the first part, the usage of a snake program. No, this is not yet all. Yeah. So this program offers some other things by, for example, measuring integrals of these signals, comparing integrals, reporting the peak positions probably, and also some fitting. But I've tried out fitting routines in here and was not that satisfied with them. I think that DMFit still offers a little bit easier analysis of spectra. So, for example, if you will have some raw data, you can use such a program like Snake to prepare a spectrum, for example, in such a form like this one, and then you simply export it into a format that DMFit will recognize. And this Simpson format is such a format that DMFit will recognize. Simpson is actually a numerical simulation program where you have as an input information the spin system, so what spins are present at what with what dipolar couplings and chemical shieldings, and then it can simulate the spectra, and it gives so calculated spectra out. But this Snake can export into this format, and DMFit can read this format, and then you simply export it into this format. But I've already prepared some spectra which we can use in DMFit before. So if you got this spectra from the organizers of this school, you will be able in the next part of this session use that spectra for analysis with DMFit. Is there anything else that I should say about it? I mean, if you want, I can let you play with this program for 10 minutes or so, or we will continue with the first example with DMFit, and after that first example, we will have a second last break. I don't know. And of course, it's also time for questions. I will stop sharing, see if there are questions. Okay, not a question, but all right. Yeah, I agree that the logo is nice. Does anyone have a question about this processing of raw data, or about solid state NMR in general? As a short pause before going to the next part of the session.
Yeah, I have a question.
Yep,
can you also do then the signal integration in the Snake? I remember from Proton NMR that you need to do the integration to know how many protons are there, and from there you can get further information.
Sure, there is probably get integrals, probably this. I must admit, as I said, this is not the program that I really work in, so I have to start index and index, start index. Okay, probably you just simply I don't know, start index, and this was now the integral for this part. And then, for example, I click here and click here, and I have the integral for the other part. So I can compare the two integrals. Okay, so it's pretty simple and pretty clear. You can do integrals here. But in this particular case, I mean, for protons, we have a problem. I mentioned before, signals overlap quite a lot in proton spectra. So, okay, what we in this case were able to do is roughly estimate the area of this part and the area of this part. But of course, often you're interested in better, let's say, more accurate estimations, and then you have to do the fitting. You have to fit with models, and this is what we will do in DMFit. This is one part of the answer, but for carbon NMR, for example, this could work pretty fine. Well, here also not where we don't have clear distinction, but at least for this part, for example, here we should get a pretty good estimation of the...
Excuse me, could you share your screen? Because we...
Aha, so, okay, I'm just doing something and you're not seeing what I'm doing. Okay, okay, sorry for that. Yeah, I forgot. Let me repeat it. I will start sharing, just a second. Oh,
thank you.
Sorry. You should warn me. Let me find which is the snake. Okay. DMFit practical. No. Introduction, number slide, chat. HERCULES practical. Is it this one? No, it's not this one. I have difficulties finding the snake. The snake, okay, perhaps, it's okay, it's here hidden. Okay, yeah. Okay, yeah. How you integrate the signals, you choose this integral button over here, and then you just click for the beginning of integration, click for end of integration, you get some number. And then for another signal, beginning, end, and you have this number here. And beginning here, and here, and beginning here, and here, for example. And for all 4 parts, you now have integrals, which if the measurement was properly done so that it is quantitative, then this should reflect the abundances of these different types of nuclei in the sample. So the number of these different type of nuclei in the sample. Of course, as I've mentioned before, when I was not sharing the screen, if you have overlap between the signals, then by simply integrating, you cannot get all information. In that case, you need to do fitting, or you need to do the decomposition. And this is what we will do in DMFit, with DMFit. Okay, I hope that you saw it now.
Yes, yeah. Thank you very much. Thank you.
Okay, no problem. Okay. Okay, yes. Good. Okay, if there are no other questions regarding the snake, we'll go to DMFit, to the first example, and then after this first example, we will do the second final break, okay? Let me start sharing DMFit. Okay, it should be this one, share. Okay. I hope you see the DMFit window. I have a spectrum loaded in, but I will load another one. We will start, for example, by proton NMR spectrum, which we just worked on also in the snake program. Now, DMFit the development of DMFit started a long time ago, probably 2 decades ago or even more. One of the main authors is Dominique Massiot. That's probably why DM is at the beginning, and was gradually improved. But still, there are some things which are not very well documented, some things which you just have to learn by trying. Otherwise, this window has this program has a main window where you see the spectrum and all the lines that you will use in the model and the progress of the fitting. And it has some buttons here on the left side where you, for example, learn what was the frequency of the nuclei for the irradiation, what is the width of the spectrum. Now this selection of nuclei must be done by the user, it's not automatically recognized. You can select the scale, whether it is shown in ppm, whether it's shown in points or hertz. I find ppm the most convenient because usually values in ppm tell me for some spectra already what kind of environment we have for certain nuclei. This graphical parameter tell us what's the region of plotting and what's the tick separation. We can, for example, decrease the tick separation and we will have ticks more often. What's important, or at least convenient for me, is that you have this checked, this each line checked. This means that when we will build a model, adding lines to the model, that we will see each individual line in the model, not just the sum or not just the current line. So this is, in my opinion, this is useful. If you don't have this checked, you can check it and it's okay. Stack means that you can plot several spectra for comparison, but you will fit only one at a time, only the first one. So we will not use it now. Okay. Okay. Now I've inserted one that I had before. Okay. So off. Okay. These buttons here are mostly for zooming in, zooming out, but they are not that useful. More useful for zooming is simply dragging a rectangle around a part of the spectrum which we would like to zoom to, and then by clicking right button we get here. Sometimes you by mistake do something like this, and then you can get back to the original view by using this mouse. Okay, I will open the proton mass spectrum, which we were previously processing in the SNAKE program. Now the format in which I've sent you, or the organizer sent you the spectra convenient for DMFit are not in such a format that the program would immediately recognize them as the ones that he uses. But if you choose all files, then it will see, for example, also this, and we will open it. Okay. Now we have this proton spectrum, and now we can start analyzing or fitting it. And to do that, we go to the composition and select new fit. Okay. When we do this, then a number of buttons appear here, and this will be very useful, and we will use them to prepare a model and to start fitting. Before starting to introduce or add lines to the model, I suggest that you here where there are question marks, that you enter the type of the nucleus that you were observing, or what kind of spectrum it was. So it was proton spectrum. This is not strictly necessary, but depending on the isotope or the nucleus that you have, of course, is the spin value of this nucleus. And for some nuclei, for those who have that have a spin larger than 1/2, some other types of line shapes are then offered. Spin 1/2 nuclei typically have symmetrical lines of Gaussian, Lorentzian, or mixed line shape, whereas those nuclei with larger spin, like for example lithium, which has 3½ or aluminum or something, can have different line shapes, and we will use that in one of our later examples. But in this particular case, we're dealing with hydrogen, so we're selecting hydrogen. Okay, now let's start building a model. To start building a model, this means we start to add signals or add lines to the model. Here we see that this spectrum should be described by several lines. We see one peak here, there's a shoulder, probably there's a line below, there's a small shoulder over here, and there are 2 more lines over here. As I said, for proton NMR spectrum, which this is a spectrum of a simple spin 1/2 nucleus, we expect symmetrical lines. If they're not symmetrical, then this means that there are several lines overlapped, right? This will not be the case for aluminum, for example. Okay, to insert the line, we push this button, so it shows add a red line somewhere. Okay, and this opened us these boxes over here, which showed us that by default, DMFIT selected mixed Gaussian, Gaussian or Lorentzian lines. There are some other types of lines possible. We will now, in this case, stick to Gaussian Lorentzian lines because it is enough for this case. And there are a few boxes where we can fill in some digits, or we can do something else. And that is, we push this button with arrows up and down and left and right. We push this button, and then we move cursor left and right, up and down, and position the first line for our model. For example, if I'm satisfied with the position, I click with the left mouse button, and then I can modify the width. I'm satisfied with the width. If I again click the left mouse button, then I will again be able to move things. And when I'm satisfied with all together, I click the right mouse button, and this line will stay in the initial model as it is now. And when I've done this, some values were put into the boxes. And the first value was the amplitude of the line. The second value was the position of the line. The third was the width of the line. The second is at the moment 0, and this, then the fourth is 0 at the moment. And this line, value tells us what's the, let's say, the character of the line. If it's 0, it's pure Lorentzian line. If it's 1, for example, if we put 1 here instead of 0, now this just typing here doesn't make the effect. To see the effect, we have to push this button 1, 2, 3, 4. Okay, and this is pure Gaussian line, right? If we do something 0.5, for example, calculate, this is a mixed, let's say, nature, mixed character of the line, mixed Gaussian Lorentzian. But we saw that before with 0, we pretty well described this tail. So these lines are, in this particular case, are quite close to Lorentzian or purely Lorentzian. Okay, so this is one line. Let's, so we still need some more lines, and let's repeat the procedure. So add a line, start position it, okay, putting it, this is okay, add a third line. I will put it somewhere here, a little bit broader, okay, it's not perfect. Of course, the closer that I will get to the proper spec, to the experimental spectrum with our model, the greater the possibility that the DMFIT will properly fit the spectrum, that will find proper model. But I hope that this will be close enough. If not, I will have to correct the starting model. Okay, and let's say the sixth line. Okay, this is the model. Now it's very crowded. If I push the snowflake button, then I only have in red the total model, the sum of all these lines, and individual IC6 lines. There are two cursors, this cross here, that tell me for which line I see the boxes here. I see the lines for the sixth, I see the values for the sixth line added. If I use these arrows, I can move to the fifth, fourth, third, second, first, or so line, okay? So, and I can modify these values if I want. And what's important, I can also modify these values if I push this button, this spreadsheet, this table. I have all the lines listed here. If I click one of them, I get the boxes with the values for each particular line. One thing which is important is to notice that some parameters are in bold character and some are in normal. Currently, amplitude, position, and width are in bold, and this Gaussian to Lorentzian ratio is in normal font. Those parameters which are in such normal font are not fitted, are not changed during the fitting. And how to decide? If I want this parameter to be changed, I need to put asterisks here. So if I change back now, I see, okay, this is bold now. But at the moment, I don't want it to be fit, so I put a space in here. So, okay, okay. If I would want some other parameter to be fixed, then I would put space instead of an asterisk. If I had a bad baseline, I could also use to fit a simple displacement or a straight line or a parabola or a third order polynomial if all four parameters were marked as the parameters that are changed during the fitting. In this particular case, we don't need that. Okay, I'm satisfied with the initial model. Sometimes it's useful, especially if you build a model that and you spend some time on it. It's good if you save the model or save the fit. So because when you run the fitting, sometimes perhaps because the initial model is not good enough, the fitting will run into a strange unphysical direction. And then perhaps you will need a lot of times again to repair the initial model. But if you saved it, you just call the previous model and slightly modify the model again and try another fit. Okay, now we have our initial model, and to start fitting, we push this bulb, this light over here. It tells us how accurate we want to be with this number. This is typically quite a good estimation. By going to smaller values, it will try to be more precise. If we go to higher values, it will try to be less precise. And if we push button, it starts fitting, and it ended fitting with the report that the fit was nearly converged. Now, DM fit will always do at most 50 iterations. If in 50 iterations it doesn't converges, then it will stop. If you see that during these iterations, the deviation, which is over here between the deviation between the model and the experiment is getting better and better and not converge, then you simply push bulb once again and continue. If you see that this doesn't work, then perhaps it doesn't go into some better direction, then you perhaps need to modify the initial model. What DMFit actually looks at is not how well the model and the experimental spectrum agree one with another, but it watches how much those parameters are changing. When the parameters which are listed here are changing for small enough amounts, then it says, okay, I'm converged or nearly converged. And when this report is given out, you say, okay, and refresh. And this is, so the red one is the calculated, the model, the blue one is the experimental, and these are the individual lines. And this is quite a nice fit, I guess. And then you can, of course, again, save it. If you want, you can export all the lines. For example, export all lines here. It says that this implementation is in progress, but it works. When you click export all lines, this means that you will generate typically an ASCII file where the first column will be the frequency, the second column will be the summed, the model spectrum, the total spectrum, and then every next column will belong to one individual line of the fitting. So you can use that data then for plotting, for example. I typically use save as ASCII in Hertz. You can save in ppm. So this only affects the first column, whether it will be given in Hertz or in ppm, and what kind of format. I usually use this for plotting, but it's up to you. This is it. Some summary of the model is given here in this small notebook under this button. These are here are the parameters you see, which are otherwise given here. But what's perhaps interesting are the integrals, which are over here. This is something I've talked before. So for such a spectrum, you can only do in Snake, you can do, if you really do integral, you can not estimate how strong is this contribution, how strong is this contribution, unless you do the decomposition. But if you do such decomposition, then you have areas under this given here. Sometimes it's useful not to read these integrals, but to say integrate model. I will show you later in which cases this is more convenient. For this particular case, there is practically no difference between the two values. Okay. This was one example. Should I tell anything else regarding this example? Of course, you're very welcome to ask some questions if you have. After these examples, I would do a short 10 or 15-minute break. I have a dry throat. I have to drink something, and we all need a short break, probably. And then we will go to 2 or maybe 3, depending on the time, additional experiments. Well, we will try to highlight. I will try to highlight some other features that DMFIT offers and that we can extract from solid-state NMR spectra. Because in this case, we only got the useful information. Mainly is we got information about the position, so about the chemical shift, and about the intensity or the integral. But in some cases, we can learn also about the chemical shielding anisotropy or the quadropolar coupling parameters, so electric field gradients, and so on. So we will do that in that further examples. For the moment, I will stop sharing this. There is one notice. Yeah, why I chose 6 peaks? Well, okay, I chose 6 peaks because let me zoom out this a little bit, because I see that this is the minimum number that I have to at least somehow model the spectrum. Why the minimum number? Because I see I can count the contributions. There is one, there is another one, there is a shoulder, so there must be another peak, and there is a shoulder, so this is a 4th and the 5th and the 6th. In fact, I know, because I know what the substance is, there should be a small peak over here, not so small as there is the difference right now. There should be a small peak given also here. But it's not obvious if you just take a look at the spectrum and count what you see. Now, it's always, fitting is always a bit, let's say it's subjective and it's tricky. I mean, if you add more signals, you will for sure get better fit. But if this is more physically relevant or not, it's a question, right? If you don't know from some other source that you need more peaks, then you generally select the smallest amount of peaks that are necessary. Because, as I said, the more parameters that you have for fitting, the better will be agreement, but more and more lines not necessarily mean more and more physical insight or better or proper description.
Oh, thanks. Yeah, I thought so. I was just wondering if that was something that you knew because you knew that it was protons, or it was just because it fitted the data. Thanks.
Yeah, it's. I mean, it's a very regular question, of course. As I said, fitting is something. Where you have to decide often. Not everything can be done automatically. Something you have the person have to decide or judge from the experience. So yeah, this is it. Okay. Okay, if there are no other questions, are there? Does anyone else have a question? If not, I propose, I don't know, shall we meet again at 16:25? Will 12 minutes be enough to drink one coffee or tea or something? Okay, great. Then see you again in 12 minutes. Okay, we're back and we will proceed with the final part of this practical session. Before starting, I wonder, did anyone of you try to do something with snake or DMFit? Did you try to follow these steps also on your own, or you were just watching the procedure? I think that some things, especially in snake, are not that difficult.
If I may, hi, I'm Gianluca. I work. I'm a postdoc in Elettra, and so I'm really not an expert of NMR. I tried a bit to follow on the downloaded version of the software, but not everything was clear to me. But it was really the first time. So your explanation and let's say the tutorial was very clear. So.
Okay, great. Yeah, if you will need, you probably have to sit and start using it, and then yeah, at the beginning.
As all the software required, let's say, and all the techniques. Yeah.
I beg your pardon, I didn't understand the last.
I mean, usually all software required a bit of a learning curve.
Yeah, sure, yeah. Okay. Yeah, thanks for this feedback. Okay, let's go to the next examples with DMFit. So this is this. Okay, here we are back. Yeah, now, sorry. Now I will open Fluorine Spectrum, which you should also get. So this Fluorine 19 MAS. Okay, open it. Okay. Now there are still parameters for the previous model, which are obviously not good now and will not be useful now. So I will choose the composition and new fit. There is also a too large number of these tick marks and numbers, so I will try to reduce these. This is just a graphical issue, doesn't have to do anything with fitting. Okay, this is the Fluorine spectrum of fluorinated alumina phosphate porous material, material similar to zeolite, zeolitic material. Now we will quite quickly see that actually this spectrum is composed of two contributions solely. So these two large signals will be two main signals or center bands, and here will be their spinning side bands to the left and to the right. And in this case, we will try to not only fit the spectrum and all these lines, but we will also try to use this information that is, let's say, contained in the intensities of the spinning sidebands and the positions of the spinning sidebands to extract back the parameters which I've mentioned in the first part in the introduction, where I was talking about contribution of chemical shielding to the transition frequency. And I was saying you have isotropic parameter, so which tells us where the, let's say, shift will be, where the isotropic contribution will be. But then we have also two other parameters. They were denoted by delta and eta. And by fitting such a spectrum, which has sufficient number of spinning sidebands, we can get this information as well. Okay, so first thing, as I said before, when we try to start fitting, let's select the nucleus that was observed. So these were fluorine nuclei. So this is fluorine MAS spectrum. Okay, and then we will start preparing a model. Sometimes, especially in the case like this, where we have spinning sidebands, it's useful if we focus just on, at the beginning, let's say on one part, take a closer view so that we will prepare a better line shape for this central part, because then the spinning sidebands should have the same shape, only their intensity should be different. But the shape will be given by the shape of these central lines, and the position will be given by the spinning frequency used during the measurement. So let's insert the first line. Okay, it will be Gaussian-Lorentzian line. Oops, yeah, okay, here we have it. Let's try to find a model. Now, you see, I'm using with this parameter for the fraction of Gaussian and Lorentzian line, the default is 0, and it pretty well describes, but not entirely. Probably this line has a bit of Gaussian character. So if I, let's say, put this to, I don't know, 10 and recalculate this, perhaps this is better. Perhaps I should even put to 20 and recalculate this. Now this is even better. And if I further slightly narrow the line, okay, this is okay. This is now pretty good. I mean, it's not necessary to be that precise when building a model. So I'm just showing you that lines can be different from pure Lorentzian, and very often in NMR, actually they are. Most of the cases which I've studied, they were closer to Gaussian than to Lorentzian, but these particular two cases have quite clear Lorentzian contributions. Okay, let's add the second line. Oh, oops, here it comes. And there we go. Now we can also already try to fit this part, and then DMFit will only use the data for the visible part. So this fitting should actually go quite smoothly, and yes, it's in a minute it's done, and this is what DMFit finds the best. I didn't mention previously, but we can inspect the difference between the model and the experiment by pushing this button where we have two spectra above and below the red line, which should be the difference. Now it's gray line. We see that there is some deviation, some difference between the experimental and the model line. And I suppose that by the shape, so the shape of the line is not very good. And this, I'm suspecting that this spectrum was not entirely properly phased when it was exported. So it has a little bit of dispersion character. That's why we don't have a very or extremely good matching. It's a good matching to determine the intensities. It's just fine. But I think that it was a little bit badly phased before it was exported, and that's why we don't get a very clear, we don't get an excellent agreement. Okay. This is the model that we have for this middle part, but then we will now we will broaden our view, and we will also try to incorporate these sidevents, spinning sidevents into the model. But as I said, the sidevents are not individual. They're not independent. They're not independent of the center bands. Their shape is determined by this shape, and their frequency is determined by the frequency of rotation. Now, if you don't know what the frequency of rotation was, you can simply try when we will open a new, add a new line and select that it's sideband. Then a box will open where you can input the rotation frequency and try where the sideband will appear. Or you can perhaps choose this button, which is should be a rotor, I guess. And then you see if it shows you where for a given frequency, which is written here below in this gray part, where sidebands should appear if rotation frequency was such as written below. And we can see that, for example, if rotation frequency was 12.5 kilohertz, so 12,500 hertz, then indeed we would get this sideband. So, and if I use the right mouse button now, the DMFit asks me if I want to accept this new value for rotation frequency, and this will be used as a starting value and then in the fitting of the sidebands. Okay, now let's add the lines for the sideband. So add new line, but this time it will not be an independent Gaussian Lorentzian line, but I will choose from here, from this menu, I will choose a spinning sideband. And when this opens, then you see all these boxes here are gray, because all these parameters will be the same as our parameters for the line to which the reference is made here. For this, currently, the reference is made to line 1. So this was the first line, so this was this line. So I will be adding a sideband for this first line, which is shown here. This is what is open. So when I will want to add sidebands for the second line, I will change this number 1 to number 2. And then we have another box, which is here, which tells us the rank of the sideband. 0th rank of the sideband would mean that actually it is a center band. But then rank 1 would be the first sideband. Rank 2 would be the second sideband. Rank 3 would be the third. Rank -1 would be on the other side, and so on. So this is, and then we have the amplitude. So I will say rank 1, and then we have the amplitude, because if it's 0, we will not see the line. But if we put something different from 0 and then push this button to calculate, okay, the line appears in here. It's a little bit too small, but let's say DMFit will be able to figure out the proper intensity. There's another box which I've mentioned before. There is rotation frequency, and it's in bold font. So we will change rotation frequency as a parameter during fitting. Perhaps this is not the most appropriate value. Perhaps it's 12.52 or something. So DMFit will try to find the best value to get the best agreement. Okay, and now I will, in the same way, add the remaining sideband. So this is a little bit tedious work. So I have to add line each time. I have to each time select that it's a sideband, but increase the rank of the sideband. And because the next sideband is smaller, I will say, okay, it's smaller. And this is the second rank sideband. And I will add the third rank sideband. So number 3 goes here, and this one's very weak, so I will put a very small intensity here. Okay, and then I will go to the, let's say, to the other side and choose rank -1 and intensity 10, and then I will add another one, rank -2, weaker one, and add another one, spinning sideband, rank number 3. Oops, not 23, just 3, and a very weak one. Okay. In fact, there is another one over here, but okay, I will disregard it right now. And I will do the same now for the second line. So I will again add a line, again choose it as a spinning sideband. But this time it will not be a spinning sideband of line number 1, but it will be a spinning sideband of line number 2. So I will put 2 over here. I will again start with rank 1. I will again start with intensity 10, for example. Okay, yes, the line appeared over here. Right, and 5 more times to repeat the same action. So this is a little bit tedious. Sometimes when you prepare such, let's say, a bit larger model, then it's particularly useful if you save the model before you start fitting, if something goes wrong during the fitting or if the program crashes, so that you don't lose the model. So you can always then recall what you've saved as a previous model. So you just go with the composition, load fit or load other, choose by name, if you have saved it, of course, and you load it. Okay, let's continue with the other part. -1 for the other side. Okay, and add another -2, 5, calculate, and add the last one, hopefully -3. Okay, calculate. Okay, let's refresh. Now we have a model. Now the deviation between the model and the experimental spectrum is, let's say, moderate. So you see this gray line, this deviation. Okay, now I will start fitting, but before that I will save fit just to be sure not to lose this work if something goes wrong. And the fitting, of course, starts by pushing this bulb, and this goes, and it said that it converged. Oh, great. Okay, so this is what we have now, and what's the difference now? Okay, the differences are now significantly smaller, but we do have this problem which I've mentioned before. You see, on one side of the spectrum, it's a little bit up, the other side is down of the line. This means that indeed this spectrum was not phased properly. So, but this is something we cannot correct right now. So we will have to live with it. Okay. So we have this result. We have the well-fitted spectrum, well-modeled spectrum. We can inspect the parameters. Now, in this particular case, it is really convenient to use this integrate model button, because for this case, as we have right now, integration takes into account the middle, the center band, what we call it, and the spinning sidebands all as one contribution. And for the second light, also all as another contribution. So it gives us result only for only 2 contributions, but the total results. So as I said, center band plus sideband intensities. And if we want to be quantitative, we should take into account all the intensity, all the area, and all these peaks. And this gives us information that the total ratio of total intensities is approximately 49% versus 51%. So we are very close to 1-to-1 ratio. And indeed, in this material, we have 2 different fluorine sites which should be equally occupied. So this is a nice result. And it also says that this part represents, in each case, in the first case, it represents about 55% of the total signal. So the sidebands contributes 45%. And in the second case, this is 53%, and the sidebands contributes 47% roughly. Okay, but okay, so from this we've got intensities, we've got isotropic positions, right? If we go here, we see isotropic position of line 1 is minus 180 ppm, of line 2 is minus 123 ppm. This is some information, but I said when we have spectra like this, we are perhaps able to extract more out of it. And to do that, we can, for example, push this spreadsheet table button, and from this list below, we select, for example, a line which is a sideband. And then we have, here we have CSA question button. This, if we push this button, then DMFIT takes the intensities of the center band and the side bands and takes the spinning frequency and tries to read from its tables that it has in the libraries what kind of chemical shift parameters would this line correspond to. And it says, okay, the closest that I come is if eta, so the asymmetry parameter for this contribution is 0.4, and anisotropic parameter, so delta in our previous lecture, is minus 42 ppm. Okay, we can just write down these values and trust them, but we can also do some other things. We can now take all these side bands and the center bands together and push this button, SSB to MCSA. And now all these parameters were gathered for the 3 chemical shift anisotropy parameters were gathered to describe a single line. Okay, we will do, I will say a few words more. We will do the same thing for the other set of sidebands. Okay, when we did this, we now ended up with just 2 lines. Okay, we have line 2 and line 1. And both of them are described only by, let's say, amplitude, position of, okay, width. These are some obvious parameters, but they're given also by the chemical shift anisotropy and asymmetry parameter. So these parameters, so these 2 parameters actually, and the rotation frequency, these 3 parameters, this one, and this one, already predict what should the spinning sidebands intensities be. But now sometimes this guessing or this determination of parameters is not good. Now we still have the calculated value as it was before when we individually determined the sideband intensities. But now if I use these parameters and calculate the spectrum, then it will be used, these parameters will be indeed used, and we can see that we still have a quite good agreement. So these parameters were quite well determined from the spinning sideband intensities. Okay, this is, this is so something additional that that can be learned from solid-state NMR spectra, and that can be done by DM-FIT to extract. Perhaps, yeah, I should note, I have enough time, I should note one more thing here. In the first step, I added a center band and many spinning side bands, and this was a little bit tedious. I could actually go the other way. I could perhaps let us delete one line. Okay, line can be deleted here. If you put the wrong line or something, we see it's too much, we can delete it here. So I will use this button to delete the line, confirm, okay, calculate, and we see we don't have a line that describes this center band and this side bands. Okay. Now to get it back, I could again put all the lines individually, or I could put a new line here, and instead of Gaussian or Lorentzian or spinning sideband, I could select this type of line. So CSA MAS. So CSA MAS is the type of line that describes center band and the spinning sidebands. But of course, to get something reasonable, I have to select the proper position. So what we get if I say, I don't know, what was it? Close, it was 117 or minus 117 or something. Let's try. And of course, amplitude should not be 0. What we get, too small amplitude. Okay, okay, this is too large amplitude. Let's have it. Okay, great. Now in a much quicker way, we've inserted all the necessary signals in here. Of course, we can still play with the width of the signal, and of course we can play with this parameter. So it was about minus 40 and 0.5. Okay. Now, of course, we can then also select in this table that these parameters will be varied, and the DM-FIT tries to fit them directly. So this is one possibility also to go. And of course, what I wanted to say, I wanted to say two more things. One is that if I don't want these signals to be treated in a, let's say, grouped way, in this case, I can use here button explode, and this will then generate, okay, this will then generate, the middle line, the center band, and the spinning sidebands. I don't know why it generated only so few sidebands. Where this was determined, I'm not sure. This is a problem. It shouldn't be like this. It should get sidebands all the way. Well, perhaps because it really sidebands really drop now. I don't know. But it should be possible to, let's say, explode these two individual lines. One other thing that I wanted to point out, this here we still have this CSA option, and I will, okay, I will delete one line so that we will better see results. Okay, let's, this is this one. Okay, let's delete this line. Okay, okay. Now we have just one set of signals, and we can just quickly check how this changes when we change some parameters. Okay, now we see we've changed the intensities. If we change eta from 1 to 0, then the sideband pattern becomes asymmetric, right? If we change the sign of this, the asymmetry parameter, then it turns the other way around. So this really affects, the shape or the envelope of the spinning sidebands gives us information on the delta and eta parameters, and this is some information about the local environment, about the symmetry of the local environment. Okay, do you have any question regarding this part? Okay, perhaps you're tired, as I am already, but we'll manage till the end, to come to the end. Okay, now I will show you an example of fitting a spectrum of a different type of nucleus, and this will be aluminum, a spectrum of aluminum nuclei. Let's say new fit again. Okay. Now aluminium. Okay, let's choose here aluminium to see that aluminium 27 is a very sensitive nucleus. Aluminium, it's 100% abundant in nature. It has moderate magnetic moment, so it's relatively. We can record spectra of aluminum nuclei very quickly. Usually, also relaxation is quick. So this is usually nice nucleus for observing, but it has one complication or added value as you want it. You can regard it as complication, but it's sometimes of added value. And this is that this nucleus has spin 5½ so it's spin larger than 1/2, which means that it has a quadrupole moment. So it is affected, so transition frequencies are affected also by quadrupolar, electric quadrupole interaction, by quadrupolar coupling, what we call it, yeah? By that term, that second term, so by electric field. And this interaction is very strong often, if magnetic, if electric quadrupole moment is strong, and if the environment is relatively asymmetric, then this interaction can be very strong. And in case that it is very strong, then also second order broadening can be seen in the spectra. And this second order broadening cannot be removed by magic angle spinning. Therefore, in the spectra of aluminum nuclei, we also we often see very, let's say, strange at the first sight lines. If we were not aware of the fact that aluminum is a quadrupolar nucleus, if this was a proton spectrum, we would think, okay, we have many overlapped signals here. We have one here, 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 and we have certainly here, here, and so on. We have many signals here. But the truth is that for this particular sample, we only have 3 different aluminum sites. But these line shapes are the so-called quadrupolar line shapes. And DMFit enables you to work with these line shapes and to fit them to the spectrum. So in order to do that, but of course that here it is important that you select proper nucleus, because only in this case DMFit will offer you these additional lines. So if we say insert a new line, then we will select possible lines. You have many possible here, but the one that we are searching for is quadrupolar, mass 1/2. 1/2 stands for central transition. We didn't have time to discuss theoretically what this means, but this is most often what we observe in the spectrum of quadrupolar nuclei. So we'll select this line. Now, if we just use this button as before to position and prepare the line, we will see that it will not very well match what we have here. So we get something very strange. Now, to come at least a little bit closer to what we have here, we first need to add some broadening. Let's say 150. Try this. What the magnitude of this parameter is sometimes difficult to estimate. You try it, enter some value, push button, calculate, and then you have what you have. Now, okay, we have some broadening, which is probably still not enough. We will increase it a little bit, but let's say to 250. Perhaps this will be too much, but it's still, the shape is way off. I mean, it could resemble such part, but not this one. But if you know the theory and the background of quadrupolar interaction, you know that, okay, what we have been changing now is the magnitude or the quadrupolar coupling constant. So if I'm pushing this button, I'm changing the position and I'm changing the magnitude. You see now the magnitude has come to 8,000. But if I'm narrowing, so the quadrupolar coupling has become, and now the quadrupolar coupling is 5,000. But we don't change the shape. But this shape is affected by this second parameter, which is eta q, which is asymmetry. And such a shape with two distinct horns at the almost each side of the line are typical for etas close to 0, whereas where we go to eta close to 1, we typically get a single horn in the middle. And this one, which we have here, is closer to this shape with eta 1 than the shape with eta to 0. But let's put it to something in between, like this, calculate, okay. And now I can also, again, try to a little bit better model this part, right? Okay, let's say that this is for an initial model. This will be sufficiently good. Okay, and then let's proceed with the second line, which will again be this quadrupolar line shape, and we will put it over here. Okay, I guess this is perhaps closer to 0.5. I don't know. Let's try it. We'll see what we bring, what we get at the end when probably it's a little bit larger. Okay, we'll put it like this. Okay, and we are still missing one line. Let's put this third line and let's put it over here. Okay, let's say it's something like this. Okay, the initial model is not perfect, but I hope that DMFit will handle it. But to be able to improve the fit, of course, I will have to let the program to vary these values. At first, I will only relax CQ and eta Q for all three lines. In the second step, I will also relax this broadening. So I go to this spreadsheet and I enter asterisks at all the values which I want DMFit to vary. So these are these for CQs and eta Qs. Okay. Okay, yeah, I didn't mention, if you perhaps opened your DMFit, it's possible that you don't have CQ here, but have new Q. So you can switch between the two representations or the two constants by pushing this button, new Q, CQ. These are actually the same parameter in different units, in units of frequency or in units of, let's say radians per second, or in angular frequency or in true frequency. Okay. Okay, now I guess I've let all these parameters to vary, and I will start fitting and something happened. Let us check. Okay. Yeah, the shape matches better than it did before, but it's probably, let's say, broadening is too large, at least for these peaks over here. So I will also let this broadening to vary, and perhaps we'll get an even better agreement between the experiment and the measurement. Okay, and let's continue or resume with fitting. Yes, the deviation has lowered from 1.7. We came to 1.1, which is a good sign. So we say okay and refresh, and here it is. So we have a pretty good match between the experiment and the measurement. And I have to make one more note here. Now, quadrupolar nuclei, yeah, they are in a way nice because they offer additional information about the quadrupolar, so electric field gradients, or the magnitude of this quadrupole term in the which affects the energy splitting. And this in turn tells us something about the symmetry of the environment, or very often also tells us something about the dynamics, because if the species in the sample is moving quite quickly, then this quadrupole contribution can be more or less averaged out. And by, let's say, varying temperature, we can see how this quadrupole term is getting more and more significant. So it's a useful quadrupolar nuclei. So such nuclei as aluminium or deuterium or so on are valuable probes. But measurements of them, although it can be quick, but it's still more tricky. One thing is that we have to take more care to be quantitative than with simple spin 1/2 nuclei. The other thing is that analysis is more difficult because these line shapes that we use in fitting in the experimental spectrum, there can be deviation from the ideal line shapes because the excitation of nuclei is not ideal. I mean, these line shapes that DMFIT, for example, uses are meant if the excitation pulses were so indefinitely, I would say infinitely narrow and high. So if the excitation pulses were delta functions, but this, of course, in reality they are, and they are have certain width and certain strength, and so excitation is not perfect, and therefore also the measured line shape is not necessarily perfect, and therefore I mean, in DMFIT you can probably not get a better agreement between the experiment and the spectrum as we did it right now. Perhaps we have some phasing problem as well, but still we may not get a perfect agreement. With some simulation programs like Simpson, perhaps, which I've mentioned before, but this is not the fitting program in the first place. It's the first place simulation program. So it simulates a true experiment. In Simpson, you can say, okay, I have a duration of the excitation pulse of 1 microsecond. My irradiation field is that and that strong, and I'm that kilohertz off the center of the signal. So it takes into account all these factors and then probably gives a better line shape, but it is way slower and more difficult to use, right? So this is the problem with quadrupolar spectra. Another problem is that sometimes when you have even more contributions, and because each contribution is not symmetrical, it can be difficult to, let's say, disentangle or to distinguish how many contributions we really have. Then we sometimes turn to more demanding measurements, 2D measurements, where in one dimension we can remove this broadening and get symmetrical lines, whereas in the other dimension we get projections which reflect this broadening. but these are, let's say, advanced topics. Yeah, okay, we can check how successful or how accurate was the, let's say, integration or the estimation of relative intensities. In this case, we see that we're pretty close to 1:1:1 ratio, which is the case for this particular material, this aluminum phosphate. Okay, yeah. Does anyone have a question now? Perhaps comment? If you have the energy, we can do another example of the deuterium spectrum, or if you have enough, I can just say a few words about the some, let's say, tools or places where you can find help for assignment of different NMR signals to individual lines. Perhaps I can first do that, and then we will decide if we go for the final, let's say, final example. But let me perhaps open carbon spectrum first to make an introduction to this part. Okay. Okay, here's the carbon spectrum, the one that was that we actually studied in SNAKE program. Okay, an important part of in the study of in the NMR study of a material is the assignment of the signals to particular sites in the molecule or in the crystallographic unit cell or so. Typically, I mean, the NMR study goes like this, that we first, with the one who prepared the material, discuss what are the questions, what's the composition of the materials, what would be the interesting nuclei or the nuclei that could provide us useful information. For example, if we have, I don't know, we were studying molecules adsorbed, so organic molecules adsorbed into a zeolite. We're trying to see how these molecules are packed into the channels of a zeolite. And then we decided, okay, these molecules have carbon, which are sensitive to NMR, proton, which have fluorine atoms. So for the molecules, it might be useful to record this spectra. And for the zeolite, which is a aluminosilicate in principle, but in our case, it was almost pure silicate material. We had silicon atoms or nuclei as an NMR active nuclei possible. And then we recorded spectra of all these nuclei. And then it is useful if you're able, for example, you take a look at the carbon spectrum and see several lines. And if it's useful, if you're able to say, okay, this line belongs to a metal group of a molecule, this line belongs to a carboxyl group of this molecule, this line belongs to this site in a molecule, this line belongs to that site. Now, some think you can learn from the areas where you get the signals, so with experience. But there are also ways in which you can help to get some, let's say, at least preliminary or some helpful information. And these are, for example, databases of solution NMR spectra, because if you have, let's say we had a molecule, perfluorinated octanoic molecule, octanoic acid molecule in a pores of the solid material, and we expect that in solution, okay, the shifts will be slightly different, but if the metal group, if we are talking about metal group, it will have resonance, it will have signals somewhere here. If we're talking about carboxylic group, it will have signals somewhere here. So databases of NMR, solution NMR spectra can also help us make the assignment of the solid state NMR spectra. So for example, some databases which I sometimes use. Okay, let me see if this is the proper window. Yes, but if I will manage to change the tab. Okay, yeah. For example, this is one of the databases. I probably ran out of time, so get back to search. So this SDBS database is quite a large database, which is free to use. You just have to agree to the terms of use, and then you enter it, and and you can search. I don't know, last thing I've typed was this, and you search if it has something with this word in the name in the database, and it has carbon spectrum and hydrogen solution NMR spectrum in a database. So in the carbon spectrum in solution, gives rise to two signals, one here and one here. And it says here, number one has about 2 ppm shift, and number two, so this carbon bonded to nitrogen, has shift of about 170 ppm. So if you had, for example, in your solid such a motif structure, such a motif part of the crystal or molecule absorbed, you would expect to have similar shifts. You might have more signals in this range if the molecules were in slightly different environments, but basically you would be able to say, okay, in this part I have this type of carbons, in this part I have this type of carbon. So databases are helpful. And here's another database which is called Spectra base, which also has some quite a large number of spectra which you can search. Then there are some programs like ChemDraw or ACD iLab. ACD iLab even online allowed free, so without purchasing the program, to use free chemical shift predictions. I don't know if this is still available. You should register there, and there you, for example, entered a mol file, a molecule, or a SMILE string or something, and then you ran carbon NMR predictor or fluorine NMR predictor, and for each individual site in the molecule, it predicted chemical shift. So this is also something you could use for help you with the assignment of the signals. Of course, such databases include only organic substances. When you go to inorganic things, crystals, and so you don't have databases, but then you have literature, right? You look for similar literature, and perhaps you learn that, I don't know, as we were, I will stop sharing this and share DMFit again if I find it. Oops, here. And for example, aluminium spectrum again, and from a wealth of knowledge in the literature, you can learn that typically signals that have isotropic positions that have chemical shifts of about 0 or slightly negative, or so in the range between, let's say, 10 or 20 to -20, that such signals belong to octahedrally coordinated aluminum sites, whereas signals which have shifts of let's say about 20 or so might be 5 coordinated. So in this particular case, we have 2 5 coordinated aluminum atoms and 1 6 coordinated. If the signal would appear even more to the left, it would belong to 4 coordinated aluminum nuclei. So some previous knowledge also helps in assignment. And then you have more demanding things like ab initio calculations, right? For example, if you have a structural model, like a CIF file, so unit cell with all the positions of the atoms, you can use this information and run first principle calculations of chemical shifts or of also such quadrupolar coupling constants. So this can be predicted in advance if you have a structural model, but this is already a serious calculation. So you have to know what you're doing. This is quantum mechanical DFT-based calculations, but there are many free packages. The ones used a lot for prediction of chemical shifts of solids is CASTEP, which is nowadays free. It wasn't for a long time. And Quantum Espresso, this is also free and very rich package, which offers a lot of types of first principles calculations of other sorts of DFT, of course. So NMR, calculation of NMR parameters is also one small part of these packages. You also have packages that also use DFT, but work not with crystalline or periodic models, but with single isolated motifs. So for if you have a single molecule and you would like to calculate chemical shifts, you can use package ORCA or Gaussian or something like this. So this is another option, which is more serious and more time consuming. And then the third option, of course, is also that you use run additional measurements. For example, as I've shown you before, for carbons, for example, you can quite quickly assign different signals to different carbons in the molecule. But then proton spectra are very much overlapped. All these shifts are squeezed into a small chemical shift range. Then it's more difficult to say this proton signal belongs to these metal protons, this belongs to a separate OH group, this belongs to something else. And then you, for example, run two-dimensional measurements where you correlate carbons signals to proton signals, or you actually examine the proximity between carbon and proton nuclei. So you get, in a 2D plot, you get a cross peak where, for example, for a given carbon and a given proton, and you say, okay, this proton signal belongs to this carbon, so it is attached to this carbon. The other proton signal is attached to another carbon, and so on. So these are all the ways which you use them to further explore your material. And then when you have the spectra and you have the signed signals in the spectra, then you typically, sometimes this is enough, sometimes you start to manipulate the sample, treat it somehow and see what changes in the spectrum. And because you know that the peak that was shifting belongs to this nucleus, you say, okay, something is going on at this position in the crystal or so. Or perhaps you study the distances between nuclei by using these dipolar coupling contributions to the local fields, and try to somehow get some information about the distances between different nuclei, and from this get some structural information about your system. So this is all advanced thing, and of course in these 3 hours we are not able to cover everything. I mean, NMR is a quite versatile, quite capable tool, but it requires some time and some knowledge and some money also. The equipment is not cheap. So please, do you have any questions, comments?